So the first paper is titled Cut Cell Microstructure for Two-Scale Structure Optimization, and presenter is Davi Tozoni, and he got a PhD from New York University and currently researcher and a software engineer in NTOP.
Hi everyone, I hope you can hear me well. So I'm Davi. I work currently at NTOP on the simulation optimization team there, doing structure optimization work. This work was done with my colleagues, Zizhou, Huang, Daniele, Panozzo, and Denis Zorin from the New York University, where I did my PhD. And I'm going to present my work on the cut cell microstructures for two-scale structure optimization. So imagine that you have this example here, which is a plier. So it's very similar to the one I have in my hands. So the idea is that when you compress on one side, you should be able to see, like what you see in pliers, as scissors, and you should be able to close on the other side. So this is what we are trying to do here. And initially, if you try to use a single material and just print it the way it is, you're not going to be able to achieve what you want. So you need to do something different. And our suggestion here is to try to modify the parameters, the material properties at each of these points to try to achieve what you want in the end, and then run this as an optimization problem and find your solution. The problem with this, if you try to optimize Poisson's ratio, which is how much a material deforms perpendicular to the loading, Young's modulus, how difficult it is to deform the material in the loading direction. The problem with this is that you're going to have an infinite number of points, so an infinite number of variables to deal with, and you're not going to be able to do this computationally. So what you usually do, you discretize the problem. So here we have a discretized number of cells. You can repeat the same idea in this problem now. You can optimize for those material properties that I said before, and then you can find a solution, a distribution of material in Poisson's ratio and Young's modulus that would fit your purpose, and you would be able to find the displacement that you want. But the problem with this is that usually printers cannot print that many number of materials. So you need to find another way to do that, because usual printers will have a finite and low number of materials to print with. Then another idea is to actually take each one of those cells and refine them the best you can. So one idea would be just to take one of those squares, divide into 4, and then into 16, until the point that you can optimize just by having or not material, which is very similar to what you do in topology optimization. And then you would maybe be able to find, but depending on the example, it would be too hard and too difficult to do that in your case. And you would have too many cells to optimize and too many parameters. You can easily go in 3D to 1 billion parameters in this case if you keep refining that, because it increases cubically in 3D. So the computational problem here is because it's too expensive to compute. So one idea that tries to mix both of these situations, that runs optimizations on different steps, in different scales, is what we call a two-scale structure optimization technique. So in this idea, we initially optimize for the distribution of material in your shape. And then each of these cells, you have different material properties that you want, Young's modulus, Poisson's ratio, for example, in that example. And if you find a microstructure that can mimic that behavior, basically these tiny microstructures that you can place inside of that cell, and you stitch all of them together, you should be able to have the same effect. The advantage here is that you can deal with these as separate problems. You can optimize for the materials, and then you can optimize for the microstructure itself. So consider that you have this dictionary of different microstructures that correspond to different material properties, and for each Poisson's ratio and each Young's modulus, you can find a different structure for you. And then you have this bar on the right side with varying Young's modulus and Poisson's ratio, and then you can use your dictionary on the left to place the microstructures in the correct place, stitch all of them together, and you obtain your final shape, as you can see here in this animation. So one real example would be this one with these 3D microstructures, and the object in the bottom was optimized so that whenever you squeeze it, it's going to flap its wings. This is the idea. Then you obtain the material distribution. Then you place the corresponding microstructures in each cell, and this is what you get in the end. You have this shape flapping its wings. But as you can see here, the shapes are usually very voxelized. The reason behind this is that it's usually easier to deal with voxels and regular grid cells when you are working with microstructures. They usually fit well with cubic cells and with square cells. But what if we want to produce, as I showed before, like these scissors, these pliers that are very curved, nicely shaped? How do you do that with a voxel grid, for example, with a regular grid? You would be able to achieve something like what we show on the right, which is not exactly what you want. And you would need to refine it a lot to actually have something that seems like the object shown on the left side, which is not something that we want. At the end, you wouldn't be able to fabricate it because you would have very tiny cells with very tiny edges, and that wouldn't be possible. So there are some trivial ideas that come from this. You could use the same coarcity that you have here, and then just at the end of the optimization, after placing our microstructures in place, you can just trim the shape according to your original shape, and then reach to this final object that you see here. The problem with this is that whenever you do that, you may end up slicing almost entire microstructures, losing the connection between them, and it may lead to very large errors in the final shape. So in the background here, you see in gray what is supposed to be the displacement of your target displacement and what the microstructure version gets with that. Another idea that is more controllable would be to, from the beginning, slice your shape, slice your grids, and obtain something that is already similar to the object, but then you set solid boundary cells to all cells on the boundary of your shape, all cut cells. The problem with that is that for coarse examples like this one, you would only have these 3 blue cells that you can optimize in the end, which is not ideal because you cannot do much with that, right? So for this 3D example, applying the same idea, in this example, we have this gripper that you apply some force on the green handle. You should be able to close the claws on the left side. If you do that, you see that on the section cut that you see on the right side, you have a very thick boundary that doesn't allow you to do the displacements necessary to close the claws on the left side. So it's not a good idea for that. There's this previous work from NYU, from our group, that the idea there was to optimize the quad mesh initially to be close to rhombic shape, each cell close to rhombic, and then we have those microstructures that fit exactly for rhombic shapes, and we can reach this very nice result shown on the right side. But this is very difficult to do in 3D because there is some challenges still in X meshing, specifically for the case of having rhomboid shapes. And the idea here is that also this idea doesn't comply exactly to the boundary. You still have these kinks related to the shape of the microstructure itself. So it's not exactly conforming to the boundary as we want. So our solution here is to use a two-family based idea. So basically you have boundary microstructures that try to reduce stiffness, that you can control stiffness somehow. And we also have interior microstructures which are very similar to what you probably already saw before in other works. And after you apply some forces on the right side, you can see that we get closer and closer on the left side. And the very good thing about this, which is a novelty in this case, is that you can also apply the same idea in 3D, which is something that you didn't have before for the other techniques. So as our contribution for this work is that we were able to build a 2-scale structure optimization for complex shapes in 3D, which is a novelty. We were also able to extend microstructures for boundary, allowing complex shapes and connection to interior cells. We also have a novel 2-stage, 2-scale optimization framework. The idea here is that we use 2-stage, so we can reduce the error. The first stage we optimize for all cells. We place the boundary cells there. And then in the second stage, we apply the optimization only for interior cells. And at the end, we apply these interior cells to achieve our final result. And the other good thing about this is that we built during this work, they smooth maps directly from material properties to geometry. This is very good because you don't need to run per point optimization after you have your material distribution. You can simply use directly this smooth map from the materials from Young's modulus Poisson ratio directly to obtain your structure using a function. Now I'm going to talk a bit about homogenization, which is a very important concept with microstructures. So in a nutshell, homogenization basically means mapping a geometry of a microstructure to material properties. In this case, we are working with nu and e here, which are Poisson's ratio and Young's modulus. So the intuition behind microstructures is the following. So consider that you have a very tiny microstructure, and then you tiled it infinitely on all the sides, on X and Y, and then you look from far away, and you're looking from far away, like in this image, you see that you almost have an homogeneous material in purple. So this homogeneous material, as any other material, is going to have some physical properties, and this would be what we call homogenized material properties. So the homogenized elasticity tensor that encodes Poisson's ratio and Young's modulus is actually the one that is mapping the macroscopic strain, which is the average strain in each one of those microstructures, to macroscopic stress, which is the average stress in those microstructures. And because we have an infinite tiling and each cell behaves the same way, we can obtain these homogenized tensors by applying tension and shear test strengths on single cells using periodic boundary conditions and compute then the average deformation. So for example, in 2D, you only need 3 of these test strengths to be able to obtain the elasticity tensor that you need. But what we are actually concerned in this work is not the homogenization itself, but it's the inverse procedure. So for example, on the right side, you have the domain of material properties that you can obtain with your family of microstructures. Imagine that you want a microstructure with Poisson's ratio equal to 0.2 and Young's modulus equal to 0.3. How do you find the geometry that corresponds exactly to that material properties, right? This is what we are trying to solve here. And for interior microstructures, the ones that we use, it's already solved. And you can actually use a method that we did before and the structures built by Panetta et al. In 2017, which are these truss-like structures, these graph structures that you basically control with your parameters, the offset basically moving around these nodes of this graph structure and increasing the radii of these nodes inside of these symmetry-based cells. And there is already some smooth material to geometry map. For this, that was done in our previous work for the rhombic cells. But the novelty here is that we were also able to extend these to 3D microstructures in this work. So we now have something that works as well for 3D mapping smoothly material to geometry. But the thing here is that it's extremely expensive to compute maps. So we use in the HPC at NYU hundreds of millions of seconds of computational time to be able to compute these smooth maps directly. And it's also a very complex algorithm to explain now. So I'm going to refer to you the paper that we did Tozoni et al. 2020, so you can know more details, or you can also talk to me after the presentation about that. Now I'm going to talk about the real novelty of this work, which is the boundary microstructures. So as I said before, if you try to use a coarse mesh and the idea of adding solid boundary cells, you are going to reach something like this, where you can only optimize 3 of these cells. So it's very difficult to work with coarcity with this method, but coarcity is also important when you're using it for printing, because you want to have enough thickness on your microstructure so you can print it, depending on your technology. So our idea then is to use different densities for these boundary cells to vary the density there to be able to control a bit more the stiffness, and then you can obtain better results with that. A safe idea of reducing the densities, the stiffness there, is actually adding holes inside each of these boundary cells with some mapping. So what we do here is that we basically use offsets in this case, as I'm going to show later. This is the idea that we used. But does our intuition hold true? Is it really true that when you add holes, you have a good mapping to reducing stiffness, for example? Is that really true? So you cannot really use homogenization here, because the boundary shapes that we have are many, and they can be even non-convex in some situations. So for homogenization, we need periodic cells, which is not our case, so we cannot use that. But what we can do instead is actually to use a rough approximation using complete square cubic cells with different hole shapes. So we did this study in 2D and in 3D. We basically vary the shape of the holes, vary the volume fraction that we are using for each one of the cells, and we have this very nice map in the end that you can approximate by a function, and then you end up having a function from volume to Young's modulus, and from Young's modulus to volume as well. So how do we do this? After we know the volume that we need, how do we build these holes? The idea here is simple. We basically use offsets. Offsets, the good thing about them is that they are very easy to compute both in 2D and in 3D, so they extend well. And the idea here is that we initially want to find what is the correct offset for this. There's no direct map from offset to volume. So basically, you compute the offset, you check the volume that you have. If you don't have it right, then you continue in a binary search mode until you find the correct volume. And that can be done quickly because this boundary cells usually have a low number of vertices. So here are some examples of what you can find in 3D with our shapes. So I'm now going to explain a little bit about our framework. So initially what we do is that we prepare these instances because we want to run simulation on this optimization framework. So for example, initially we have this grid and this surface shown in blue. Then we use a triangle meshing or tetrahedral meshing procedure if we are working in 3D. And we want a procedure that tries to approximate the surface preservation in this case, because when we want to keep that blue surface as part of our meshing. And then at the end, we basically compare the barycenters of each of the triangles or tets and see if they're inside or outside of your blue surface, and then you remove if they are outside. And then you have something that you can work with in the optimization step. We also classify the cells after because some of them are going to receive boundary microstructures, some of them are going to receive internal microstructures. So we need to do that separation. So for the boundary cells, we take the ones that are touching the boundary and directly, and we also take into consideration the technology that you are going to use to fabricate your objects. So for example, if you have a minimum thickness in your printer that you are allowed to print, then that can be used to verify if some of the interior cells are too close, for example, to your region. That can also help to prevent buckling, for example, because these joints in the boundary shown in black here, they can damage your final results in the end after you fabricate. So after you prepare your instances, you can run our two-stage to-scale optimization. In the first stage, as usual, we are optimizing the material distribution in each of the cells, considering the constraints that you have on each of the cells, the material constraints. Then we place the boundary microstructures already there in those cells, and we run again the optimization. The advantage of the second optimization is that we already know, we already have the mesh of the boundary done for us. So we can use that information to reduce the error. And here's our optimization problem that we run at each of those stages. Is a PDE constraint optimization. You can see on the right side that we have the elasticity PDE there. And our variables in the optimization is this tensor C, which basically encodes Poisson's ratio and Young's modulus, for example, in our case. And we have two different terms, the matching target displacement. So the idea for the pliers, for example, what you want is that whenever you press here, right, you're going to close on the other side. So this is basically your target displacement that you want to match when you simulate. And also we have a material smoothing term. So we don't want to have large changes in geometry. And because we are using a smooth map, we don't want to have large changes in material when we build this material distribution. And we also need to take into considerations the variable bounds in this optimization problem. So for the boundary microstructures, you have from 0 to 1 Young's modulus, and we have that triangle for the interior coverage, as you can see there, for Poisson's ratio and Young's modulus. It's also important to take into consideration fabrication details. For example, what I already said before about the minimum thickness that you can print. Otherwise, you may reach problems like this. That you can see that some parts of the shapes in the microstructures are disconnected. So you can try to limit that by using a minimum value for Young's modulus, for example, in your construction. And also, depending on the technology that you're using, 3D printing, for example, you cannot have enclosed voids. So to remove the excess material that may be there, in the end, what we do is that we build these connected pipes inside of these boundary cells and also connect them to the outside and to the inside, so you can also remove material from the inside, from the interior microstructures. And I actually have the example here. You can see these dots, these little dots that are there, is basically what I shown in the previous slide, where you can remove material from. So computational results and evaluation. So we compared with the trivial methods that I explained before. So on the left, you can see the trimming grid cells is that idea of basically optimizing, placing the microstructures, and after all, you slice according to your original shape. As we shown before, that algorithm has some issues, and you can actually see the tip of the zoom tip on the top, showing that you are not actually getting closer and closer with that side of the pliers. So you're not achieving your objective with that. So for the solid boundary idea, you get better results. You can see that it's closing, but it's not closing as much as we wanted. But when you are able to reduce the stiffness on the boundary with our method, you're able to close, and you only have 1 millimeter distance between your two sides. We also experimented in 3D with the gripper that I showed before. So the idea is that in our case, you can see that the claws on the left side, they close much more than when you use solid boundaries. Here are some practical examples, some examples that we printed as well as the one that I'm holding here. So this plier, the idea is that we have the material distribution on the left side, and this is the simulation in the middle. And then I also made a video here that you can see how this works in real life. If you open the handles, it's going to open as well on the other side, and if you close, it's going to close the same way. So you can hold small objects, and you can play with it. We also built this bird example in 2D. The idea here is basically that we want, as the initial example that I showed that was very voxelized, we want to, whenever you compress it, whenever you squeeze it, it's going to flap its wings. You also have the material distribution and fabricated example that we also have here if you want to see later. We also have this other gripper. That the idea here is that it's in the form of a sword almost, and if you fix that yellow region, you put a directly constraint there, and you move the guard of the sword up, you should be able to also hold objects like you can see there on the right side. I use a drumstick to kind of hold that into position to make it work. Yeah, so you can move up, you get the object, and then you can slide holding the object. And finally, we are able now to also use the same technique in 3D, which is something that we didn't have before. So it's very cool to see the section cut because you can actually see how the microstructures are inside of the shape. And you also have the material distribution here, and then a simulation on the right side after you press the handle, what happens. We also have a bird in 3D to compare with. Again, we have the material distribution, and you can see internally with a section cut how it works inside, and as well the simulation how it works. We also fabricated some of these 3D shapes. We have a simplified version of that gripper that I shown before. The idea is that if you press in between, here you apply a force in between these claws, the claws are going to close, as you can see here on the left. And we also have a bar that whenever you compress, it's going to produce this sine wave shape. I also have it here if you want to take a look later. So as a conclusion, we were able to build this complete 2-scale structure optimization framework, which robustly produces optimized shapes of complex geometry boundary in 2D and especially in 3D, which we were not able to do it before. Our code is going to be online soon. We're just cleaning it up. And as future work, it would be interesting to use different families of microstructures, maybe trying to have families that are more similar to each other from the boundary to the interior, trying to reduce the connection that is very different between them. Also using nonlinear elasticity, which is a complicated thing to do because you can use that for the material optimization side easily, but on the microstructure side, homogenization with nonlinearity is a difficult problem. Also adding contact, because what happens when you compress these objects and you change the shape of these microstructures during operation, they are going to have self-collisions. They're going to contact with each other, and is also something important to do. And also include buckling and displacement smoothing. As I think you were able to see in some of the experiments have some buckling going on, so we need to treat that better. And maybe smoothing out the displacement is a good solution for that. Thank you very much. Hope you appreciate it.
I think we have time for a few questions from the audience.
All right, thank you for the talk. You mentioned, so you're optimizing ultimately over the elasticity tensor, but you said that it encodes the Young's modulus, et cetera. So are you modeling this purely as isotropic elasticity, or are you also modeling like general anisotropic cases?
The same idea could be used for orthotropic materials, for example, but we use in our experiments, and including previous work, only isotropic microstructures. We have a way in the way we build the smoothing map, the smooth map from material properties to microstructures to guarantee that the result is going to be isotropic. So all those microstructures that you saw, they are isotropic by construction.
Okay, thank you.
Hi, it was very cool. Can you go to slide 49? Right. So I noticed that, the picture here, the second and the third one, the place where the gripping, the thing that you want to do occurs, right? The thickness of your boundary is different. But then, on slide 52, sorry. This one is symmetric, and I would argue as a person who used pliers, like this one's more like what I would expect.
Yeah.
And so, what is the process in which one can ensure that my result looks more like this and not the one on 49, where it's asymmetrical, and one of the boundaries is arguably functionally like a little bit thin for comfort. Like how would a user like this like make sure that it's of this type?
Mm-hmm. Yeah. Thank you for your question. Yeah, I think the general idea of how you can do that is that from the beginning you could have, for example, initial mesh that is symmetric, right? Like if you have a mesh that is symmetric, you're going to place the microstructures and it should be all fine. You can also use optimization there to kind of make sure that after you have like a symmetry constraint there in the topology optimization, the material optimization case, trying to make sure that the material on both sides are the same. You can also prevent thickness adding, as I said before, depending on the technology, right? You want to limit because of the printing thickness, but you can also limit just because you don't want that thickness to happen, right? Like you can also limit just depending on the user needs, right? We actually did that on purpose, like to try different models like shifting, because we want to show that our method behaves well if you shift and it doesn't matter, as other algorithms maybe are not going to work as well, and depends a lot on the meshes. Our method, we believe it doesn't depend as much on the mesh itself.
So if I understood what you were doing on the boundary voxels, you made a simplifying assumption in analyzing them that you treated them as if they were the full cube, even though they were some fraction of that, and then analyzed that to get. Do you have some bound on the error there, or what the impact of that simplification is?
Yeah, so what we did was to consider that as a rough approximation. We are not, of course, it's not going to be a direct map, right, from what really happens in those boundary cells. But we believe that our second optimization stage, this is why it's two-stage optimization, is going to fix any inconsistencies that you have there. Because after you have the boundary and after you place those microstructures, you are still going to be able to optimize the interior cells. So you can reduce the error that comes from that assumption that they behave similarly to square or cubic cells. So you can do that. Thank you.
Hi, I appreciate the talk.
Thank you.
Just quick question on your 2D example. So how do you have any assumption in the third degree of freedom? How does it affect your result? I suppose the thickness of it will introduce additional Poisson's ratio, additional shrinkage. So in your calculation, does that affect, how thick, your prior, where it was, going to change the results?
You mean like if the Poisson ratio would also count?
Right.
Yeah, that's a very good question. I think it would count, but our assumption is that stiffness, that Young's modulus is the main player here. So we are assuming that. But you can also directly go and restrict on the thickness side directly. And whenever you map back to the structure, you can assume that you have a minimum there. And then you can always even in the map beforehand, you can restrict the Young's modulus that you can get. For example, what I shown before is that you can go from 0 to 1, right? But it's not real, you cannot really go to 0, right? Like, so you need to have some restriction on the material space as well, and then you're able to handle these cases. Thank you.
Hi, if you go back a slide or two to the little 2D bird that you had,
Which one?
I think it was a slide or two back or forward. You had a little 2D bird that you squished.
Oh, yeah.
That one. So it looks like a designer has basically modeled some eyes and a beak in there manually, right?
Yeah.
So does your system take into account the effects of that?
It takes into account because the optimization uses simulation, right? So it's going to simulate, and if that somehow is going to try to provide some cells around it to fix any behavior that those holes are providing to the final shape.
Okay, thank you.
So it basically simulates, and if it's not good, it's going to change the material properties. So it takes into account everything. Like, thank you.
All right, our next talk is on shape design and optimization of gerotor pump, and presenter is Juan. He is a researcher in Tech Foundation and also a PhD student at the University of Barton.
Okay, thank you, everybody. I'm going to present this work that we did at Tech with my PhD advisor, Michael Barton from Becca. Okay, so I'm going to talk about gerotor pumps, so I'm going to just give a little bit of an introduction because probably you haven't heard of this. This is a gerotor pump. A pump, as you probably all know, it's just a device that moves the fluid around. You have a lot of different kinds of pumps, but in this case, the gerotor pump is an internal gear pump. This means that you just have two rotors, and one of the rotors, the internal one, just moves inside the other one in hypocycloidal motion, and this motion compresses the fluid in the chambers, and it expels the fluid in the direction of the axis. These kind of pumps, they are very popular in all sorts of industries, medical, aerospace, automotive, because as you can see, it only has these two main moving components. So it's very compact, and it's very reliable and easy to use. Here I have just a little bit to show you in motion how it works. As you can see that the external gear, it has, in this case, it has 5 teeth, and the internal gear, it will have 1 less teeth, in this case 4. So the fluid enters the pump through the green region, it is compressed, and then it's expelled from the pump in the red region by this compression of the chambers. So the important thing here is that as the pump rotates, we wanna calculate how much of this volume in the chambers reduces, because this reduction is what actually pumps the fluid out of the pump. So we want to optimize for this. We want to see, okay, we want a pump that pumps out the maximum amount of fluid possible, and we want to tweak the different profiles around so that we can have the best performing pump possible. I'm going to show you here how to generate the internal profile of the pump. You see in this slide that we have 2 rotors, and each rotor is defined by a curve. In 3D, they're just extrusions of these 2D curves. So in general, there are a lot of possible constructions, but I'm going to show you the hypocycloidal motion construction, which is probably the most used in industrial applications. Here we have the profile is going to be defined by tracing in time this point R, which is this red point here, and the way that this moves is that this circle C1, which is the yellow circle, it will start to move inside, rolling without slipping inside the red circle, which is hypocycloidal motion. And this, when this moves, you have to trace a line from the center of the static circle, the red one, with length R2, which is one of the shape parameters of this curve, And at the end point of this line, you have to build this circumference with radius s. And as this moves around, you know, the instantaneous center of rotation, it will change. It will be in different positions. So for each position, you just have to intersect the line between the instantaneous center of rotation, the I, and the center of this circumference to get the point R. So as you trace this motion around, you get a parametric expression for the internal curve of the gerotor pump. What you will see here is that this entire construction depends only on these three parameters. They are bolded here. This is the eccentricity, which is the distance between the two centers of the two this moving circle and the fixed circle. The R2 length, which is the length of this line we build, and the S, which is the radius of the circumference that we build. So with these three parameters and the set, which is the number of teeth that we want, we can build any pumps. So we show here just how these different values for these parameters actually produce very different profiles. And these will be pumps that will have very different performances, outputs, and in general, just very different behavior. Okay, but so far we only have the internal gear. We want to be able to build in an efficient manner the external gear, the curve of the external gear. So we have to consider how this internal gear will move to be able to find how this external curve should look like. And the way this moves is that we consider the same two circles that we had in the first place, the moving circle inside of the static circle, and we fix this, our internal curve to the moving circle, and we let it move around in this hypercycloidal motion, and we will have just a family of curves in the plane. These are like the different positions of the curve along its movement, and we represent this by this bivariate function in terms of theta, which is the angular parameter of the curve of the gerotor internal profile, and the phi parameter, which is time or pseudo-time. We can visualize this motion as a surface where we have, you know, the xy axis, we have the phi parameter, which is time, the vertical axis, and if we consider this movement as this surface, then we can just, you know, say things about it here. We can have these green curves, which are just the traces of a single point in time. These are when we just set the theta to constant, and we have these red curves, which is they are the gerotor profiles at some time instant, where we just fix the time parameter. But what's important here is that we see like a top view of this surface. We project it to the xy plane, and the external curve of the gerotor will be this outermost envelope. So we want to find some efficient way to calculate this outermost envelope, and that's our main objective in the first part of the paper. Notice here, it's important here that when you project this surface to the xy plane, you have an internal envelope, which is like the internal part of this region, but we don't need to calculate that, but we will see how to separate those two later on. First, we have to define an envelope condition. How do I know that a point in this surface will be on the envelope? Well, it will be if its tangent plane projects to a line in the xy plane. So what we have here is just an example. We show the gerotor profile at some time instant phi equals pi, and we show this point P, and we see that if this point P, we can calculate its tangent vector, its tangent plane. We have this, we can differentiate our bivariate function that defines the surface and find this n vector, which is normal to the surface at that point. And if this vector is parallel to the xy plane, I know that this point will be on the envelope of the rotor as it moves around. But what this, and we can express this as, you know, this formula in the 2D moving curve. But what this doesn't tell us is if we should, this condition will be met by points in the outermost envelope and in the internal envelope as well. So we need a way to differentiate between those two. An important and a curious thing about this is that if you consider the points in this surface that solve this envelope condition, you can classify them into three groups. You can either have them on the convex parts of the curve, which are the magenta points. You can have them on the concave parts of the curve, which are these green points, or you can have them as the inflection points in this curve, which are the blue points. We showed that these points actually correspond to local maximizers and local minimizers of the distance function between the curve and the instantaneous center of rotation. So this is like a very fast and easy way to calculate these points. You're just looking for these local maximizers and minimizers. Some facts about the envelope is that you will have this contact between these two curves, between the internal profile, which is this R theta curve, and this E0, which is the external. It will happen at Z minus 1 points, and it's continuous. So in continuous is important because you know that the contact points, they will not jump around. The contact point for some time instant will be in the vicinity of the contact point for the previous time instant. They are rotational symmetric. Both profiles, they are rotational symmetric, so we can study the trace of only one contact point. If we can sort of trace this contact point throughout the movement, then you can recover the whole curve just by transformations of this calculated segment, so it's easier that way. And the most important realization here is that the concave parts of the external envelope, they can be generated by both the convex parts and the concave parts of the internal. When you look around this and this is moving, you can see that the concave parts of the external envelope, they are touched by both kinds of points in the internal curve, but the convex parts of the external envelope, they will only be generated by convex points of the internal curve, such as the one here on the left, where it's just not possible that you will have contact between this part of the external envelope and some concave point in the internal envelope, in the internal profile. So we solved this by root tracing. We want to find, okay, we know that we have the equation that all points on the envelope must comply with, so we just trace solutions for that, for those points, but we reduce the domain. And this domain reduction is actually what allows us to make it faster, because we know, okay, we just want the solutions that are part of the convex regions of the internal profile. We do not care about the other parts, because they will never touch this external envelope. So for some time instant, we just solve this equation. We use a Newton-Raphson method in using the previous contact point as initial guess, because we know it's continuous, so the contact point will be in the vicinity of the previous one, so this will have very, very fast convergence. And we show here the difference of using this reduced domain with respect to not using it. For example, in the left, we show how it will look just by applying the envelope condition like without this reasoning. This is the Podman-Peternel's approach, and you'll see that you start to trace these internal points as solutions to the envelope condition, and then you would have to do something to filter those out, and we want to avoid that in the first place. We don't want to filter them out, but by using this convex reduction, then we can just not generate them in the first place, like we do in our method. Okay, so let's see some of our results. We show here the results for our envelope algorithm. We can calculate the correspondent conjugate curve to the internal profile, and for different values of the shape parameters. And we show also, in the frame values, we show the cavity area, which is the area of the fluid, the one we want to optimize, which is different, like the difference of the area enclosed by the external and the internal profile, as a percentage of the internal gear area, because this is important to know, like, okay, there are some pumps that have better properties for the shape parameters in terms of the fluid area. There will be, these cavities will be filled by fluid. So this is the most important measure for us to be able to optimize the flow rate of the pump. And then we delve into the optimization. We want to maximize the amount of fluid pumped. We want to maximize the size of these cavities. And we are going to use a geometric proxy variable for this because, well, the cavity area is not quite the flow rate of the pump, but they are proportional. I mean, you can see that the flow rate of the pump is, I know, liters per minute or gallons per minute. And this is just the area or volume of something. There's a velocity vector there that's missing, but they are proportional, so it's a good enough measure of the flow rate. And we have two constraints. These are engineering constraints that came to us by the specific engineering problem we are trying to solve, which is that the area of the internal gear must stay constant. This is, we want to keep the amount of material needed to manufacture the pump constant. And we want to keep the weight of the pump, which is mainly given by this internal gear, which is like the most massive part of the whole set. We want it to stay constant. And we want the size of the gears, which is given by the R2 parameter, allowed to vary just within a 1 millimeter range. So we want to keep the size of the pump pretty much stable in this 1 millimeter range. And this is because if you want to, for example, you have an existing pump, it is embedded in some system, it does not exist in the void. It is in a jet engine or it is in a helicopter engine. So if you want to replace that pump with a better performing pump, but you need to fit and do not disrupt your whole system. By this, we estimate the area of the internal profile just by like a sampled polygon with some step size. In the paper, we show what's the needed step size just to have the same results as numerical integration. But the important thing here is that you build this expression G, which is the area of the internal profile, as a function of the shape parameters, so you can actually use its derivatives to speed up this optimization. So if we think in terms of these shape parameters, this will be like the shape parameter space. So we have this space with R2, S, and E. And we want to know, okay, how does this look like for a constant area manifold? So we build this manifold, which is a surface in this shape parameter space. And every point on this surface will have the exact same area for the internal gears profile. But as you can see here, we do this for several values of the teeth of the pump. And if you look, for example, as E increases, the manifold, it behaves well, it's well behaved, and then all of a sudden it just goes crazy. And we saw that and thought, okay, there's something missing, and it's that not all the values of the shape parameters, they produce physically feasible gerotors. And by physically feasible, we mean curves, internal curves that do not self-intersect. So it's actually very easy to find combinations of these parameters that give you self-intersecting curves. So we have to somewhat avoid this behavior by adding a constraint. And we ensure this by using a well-known result in gear theory, which is Litvín's singularity condition, which basically tells you what are the relations between these shape parameters that you always need to have to avoid this kind of singularities. And we want to see how this inequality shows into the shape parameter space. So if we go there, we have this inequality with these two bounds, and these two bounds, they correspond to hyper surface in this shape parameter space. And this omega f, which is like this volume enclosed by these two hypersurfaces, will be feasible space, which means every point in this space, in this volume, will be a physically feasible gerotor. It's something that can actually be built, and it makes physical sense. But we still need to intersect this with our constant area manifold, and by this intersection, then we have our constraint search space, which is this surface in shape parameter space where we will have not only gerotors that are the same area for the internal gear, but also that they are physically feasible, they can be actually built. And if you do this intersection for different values of the teeth number, then you can see that this strange area behavior disappears, and you have well-behaved search manifolds. And each point on these manifolds, we just have to find which one is the best within these manifolds for our gerotor. So what we do is that we take a piece that exists, it's used in helicopter engines, and we want to find its equivalent, and by equivalent I mean same internal gear area and just this little variation in size, but that hopefully it's better in terms of fluid area. From the left one picture you cannot see that much, but if you look at the compression chamber, you can actually see that the optimized one, the red one, is bigger. It's noticeably bigger than the original one. This means that we will have more fluid allowed in, and we can pump more fluid out of the pump. To validate this, what we did is, okay, we need to find out if this optimized pump is actually the better one. So we sampled the search manifold with around 5,000 samples, and we just measured which one was the maximum value, which is the color code corresponds to the fluid area, and they differ just by 0.11%, which is good for us. But the most important measure here is simulation. I mean, you have to simulate these profiles and see, okay, is this actually better in terms of flow rate, not only fluid area, but flow rate itself? And what we can say is that our optimized profile actually increases the flow rate by 16% with respect to the original piece, which if you see in the image on the left, the original one was not a bad pump to begin with. It was already a good pump because it's operational right now, so it's supposed to not be bad. So this is like a very fine tuning, but this little change in the geometry of the pump actually can produce an important increase in the flow rate of the pump. We did some physical validation by printing this in plastic. Obviously, you cannot say a lot from this because you would need to manufacture it in, I mean, aerospace, steel, and actually put it in a test bench and measure the flow rate. And this is expensive, it takes time. So what we did as a first step is to just 3D print it in plastic and see, okay, to validate at least the kinematics of it so that it moves smoothly around the external pump. We have some sort of video comparison here. The movement is as smooth as we would have expected from both. And okay, as a matter of conclusion, we presented an efficient algorithm to calculate the envelope of the gerotor profile by this convex decomposition of the curve. We explore the optimization, how does it look like in the shape parameter space, and our optimized pump increases by 16% the simulated flow rate of the existing pump. For us, what's next is physical fabrication. We want to test this to industrial standards. I mean, you cannot say much about it with plastic prototype. We want to test it in a test bench and see if this 16% simulated flow rate increase actually translates to the real world, which is where it actually matters the most. And as these pumps, they are rotating at 10,000 RPM, what would follow for us is just including the mechanical phenomena, contact stresses, which are important when we talk about these fastly moving components. And that's it. Thank you for your attention.
I think I can start with one question. So is your method sensitive to initial gas, assuming you have different ionization power to the same result, or they are very different based on the initial gas?
If you're having gas instead of fluid?
Yeah, you have initial parameter you can start with. I mean, the initial value you start with. So start with, are they very sensitive? apply impact to the final result?
I'm not sure. I mean, if the,
Try to use a different parameter to start with from your optimization and as it convert to the final result?
oh, yeah. By, you mean by the initial point of the optimization? Yeah. We have tried different initial points, and it will come to the same result. As we saw, the function is very well behaved in the search manifold, and actually this tells you that you could have some thumb rule that you can increase the eccentricity in your pump and have the best possible pump for you. But we did not know that before. I mean, that this is so well behaved in this search manifold tells you that the engineer can say, okay, I want to have the biggest eccentricity I can have without breaking the slit bins condition, and this will be already a very good pump, probably near the optimum.
Yeah, so I saw you optimize result very close to the initial shift.
Yeah.
Which means the engineer already know what kind of
Yeah.
look like.
Yeah.
All right, thanks for the
Yeah, thanks. That was a great talk. This might be more of a general question about these pumps in general, but you started the talk by saying these pumps are meant to compress fluids, but then you were optimizing over the area. Does the shape of these envelopes tell you anything about how much the fluid is getting compressed? And similar to the first question, do you need to take into account like the physical properties of the fluid you're actually trying to compress?
Yeah. Regarding the first question, it's by the way the gerotor works. If you maximize the area if you look at this slide, for example, at the first one, if you for example, here we have the compression chamber for this part, but as the gerotor rotates, this will come to the point where this chamber will be of near zero area. So if you maximize this area, this fluid cavity area, at some point, and you know that at some other point in time it will be near zero, so all this fluid went out of the pump. So it's like a way to ensure that this is going to be a good function to optimize.
Thank you.
I will ask another. Oh, yeah.
I can imagine that in some applications it's not just about the magnitude of the flow rate, but also about the constancy of the flow rate. So that probably is some kind of condition on the derivative of the area. Is that something you could potentially easily take into account, or would this be a completely different matter?
No. That would be, this is actually done in the literature. This is known as the flow rate ripple, which is just how wobbly the flow rate is. And some people optimize for it, but for different applications. I mean, this flow rate ripple is related, for example, to the noise of the pump. So some people in some applications that need very like pumps that make no noise at all, they optimize for this. It can be done, but it would be like our contribution actually can help with that because we build the external envelope in an efficient manner. So you just change the objective function in this search manifold, and you, instead of area fluid, you go with flow rate wobbliness, flow rate ripple. You would, of course, have to have some simulation to be able to build this objective function, but it will be possible, yes.
Thank you.
Yeah, I think we'll have a last question relevant to the flow rate. So if I have, assuming if artists want to design some particular flow rate profile, do you think if we increase the design space, so could we potentially optimize that based on the flow rate profile?
Yeah, at the moment we do not take into account the fluid's properties, but I mean, because in this kind of pumps, at the kind of velocities they operate, some very strange things happen, like aeration, cavitation. There's a lot of hydraulic phenomena. So it's very hard to have like a geometric optimization with this kind of fluid parameters. So we do not take this into account because that would require some sort of CFD-based method, which is like out of our range. Yeah.
All right. And the presenter is Jiahao, who is PhD in the University of Southern California.
Yeah, so thank you for the introduction, and hi everyone. My name is Jiahao, and I'm glad to be here to give a presentation of our TVCG paper, Large String Surface Modeling Using Plasticity. And this paper is the work of the collaboration between USC and MIT. So before introducing our method, I would like to first show you some videos to give you an intuition about what's the problems we are trying to solve. So this is a neutral mesh of a fish, and our method can gradually grow the mesh to meet the user constraints. The red dots here are the undeformed and the deformed user constraints. And more specifically, our method computes a large spatially varying non-uniform scales to meet the positional constraints. And the scales are isotropic and also arbitrarily oriented. So it should be noted that here we are focusing on the large non-uniform scaling, so this is quite important. And here is a visualization of our result mesh from the different angle of views. And you can see our mesh is indeed quite smooth from the different angles of views. So our project aims to make the shape editing as smooth scaling as possible. And we gave a new shape deformation method for the 3D triangle meshes that satisfy the following properties. The first one is that it's rotation aware. And the second one is that it supports the arbitrarily oriented scales, and usually they are non-uniform. And the third one is that in our method, the rotations and the scales vary smoothly across the whole mesh. For example, here we show how to use our method to rotate and stretch the double wings of the eagle smoothly and gradually. And in our framework, users can give their positional constraints or the rotational constraints, and our solver imposes the above properties in the final result. So here is another example that our method can deform the template muscle to match the realistic MRI scans. So we got these red dots positional constraints from the realistic MRI images. And here is a visual comparison of our method to other methods. So this is our result from the different angles of views. So you can see it's quite smooth. But here we compare our method with some shape editing methods like shape help as rigid as possible and primal. Yeah. And you can see our method produced a visibly smoother silhouette than the shape help. And for the as rigid and possible, for the as rigid as possible and primal, actually they suffer from this kind of sharp artifacts. All right, so here is our rationale for the method. The users intuitively expect that the shape editing preserves the intrinsic original shape. And our method can accommodate this because our scales and rotations vary smoothly across the whole mesh. And most of the previous shape editing methods, they are not designed for this purpose. So that's why the standard method produces spikes, wiggles, or other artifacts as opposed to smoothly scaling the object. So here we run these 3 papers, we implemented them and run the results. And so here you can see they all suffer from these sharp spikes near the positional constraints. And some papers are indeed designed for the same purpose, such as shape up. And the shape up can smoothly scale the object, but we can prove that the results are quantitatively and qualitatively less smooth than ours. So here you can see this is a comparison in the horse experiment. And we want to bump the back of the horse. And in the result of the shape up, we can observe a weird stretching in the belly. And also for the statistics, if we do a statistic about the curvature change, our method can have a lower mean value and also a lower standard deviation. There are another series of related works focusing on the volumetric meshes. So all of these works use the element-wise input parameters to define the target shape and obtain the output mesh that meet user constraints through the optimization. And all these methods can be used for the anatomy transfer or the shape targeting, and so do we. But the difference is that our method can work for the triangle meshes in 3D. All right, so among all these works, Wang's paper in 2021, so they are the most relevant paper to us. So in their paper, they use plastic strings to model the change of the elastic rest shape To be more specifically, they have a 3x3 symmetric matrix for each tetrahedron to change the plastic shape or the target shape. And then they run the static equilibrium to get the final output. So here the logic is that, so given the input mesh, all these methods can apply the element-wise degree of freedoms to the triangles or to the tetrahedron. And they can define such a plastic shape or the elastic rest shape or the target shape. And usually under user constraints, this kind of shape cannot be achieved globally. So they need to solve the static equilibrium to get the final output. And our method follows this logic. So the framework is almost the same. But we need to emphasize that. So here we say plastic, but we don't really mean that we are running some plastic materials or we are doing some plastic simulation. So plastic is just a concept of that. We are trying to define some target shape, and this target shape cannot be achieved, so we need to run a simulation or to run the static equilibrium to get the final output. So the previous method still have some problems. The first problem is that it only works for the volumetric mesh, and also it only handles the large strings but no rotations. And third problem is that it's very slow. And we address all these problems or improve them in our paper. So here is the visual comparison of our method with Wang's paper. So the left mesh is a template muscle, and the blue or the red dots are the landmark constraints. We obtain them through the MRI scans. So our method can produce very similar results as Wang's work, but our method can work on the surface mesh. So there is a big gap between the volumetric mesh and the surface mesh. Actually, it's non-trivial to overcome this gap. So to overcome this gap, we actually need to solve some technical challenges. The first technical challenge is that we need to answer the question, what is the correct deformation space to express arbitrary scales and rotations? Because we know that for the triangle meshes, your elements are triangles, so you cannot just copy-paste the same idea to apply to the triangles. And the second question is that how to enforce the smoothness for the triangle mesh in the output. So our key idea is that for an arbitrary point on the continuous surface, we can actually define this local frame. So this local frame D includes 3 directors. The first 2 are T1 and T2, so they are the tangent vectors, and they can span the tangent plane. And they are not necessarily orthogonal to each other. The third director is actually the normal vector on that, on that point. And our modified local frame will be multiplying a rotation matrix on the left side and also a scaling matrix on the right side. So here we know that the deformation gradient is the capital, the D bar times the D inverse, right? So, sorry for the typo. So here it should be D times the D bar inverse. So actually we can changing the D bar by to deform the surface locally. And in short, our key idea is that we locally modify the surface via a 3x3 rotation and a 2x2 symmetric matrix. And here, the 2x2 symmetric matrix represents arbitrarily oriented non-uniform scales in the parameterization space. And both R and S are spatially varying. So at the first glance, you may think that this method is quite similar to the standard polarity accommodation, but actually they are different. So one difference is that our scaling matrix S is a 2x2 matrix, and it applies in the parameterization space. And we also verified the standard polarity accommodation, and it turned out that it didn't work. So we will introduce the result later. So this is our modified local frame, and now we can count the degree of freedoms for each element. The rotation matrix, the 3x3 rotation matrix, includes 3 degrees of freedoms. And the symmetric matrix, because it's a 2x2 symmetric matrix, so it also includes 3 degrees of freedom. So totally, we have 6 degrees of freedoms for the local surface deformation. All right, so I just introduced how to use our degree of freedom to change the local frame. And now we can also modify the first and second fundamental forms accordingly. So this is the shell parameterization. For an arbitrary point on this thin shell, actually the position of that point is simply the corresponding position on the mid surface plus a small offset in the normal direction. So R here, the right R here is actually the mid surface, and N is the normal vector field. So through this parameterization, we can derive the parameterization gradient for both the mid surface and the normal vector field. Here, to be clear, that this capital F doesn't mean the deformation gradient. And sorry for the confusion, but this capital F means the mid surface parameterization gradient. And with this capital F and this capital N, we can define the first and the second fundamental forms accordingly. And both the first and the second fundamental forms, they are the 2 times 2 symmetric matrices. And with our R and S degree of freedoms, we can modify the mid surface gradient and normal derivatives to the F bar and N bar. So for the F bar, it's simply the RFS. I think this is the most elegant equation in our paper. And the capital N bar actually is a quite complex function of R and S. So you can see the details in our paper. And because we change the parameterization gradient for the mid surface and normal respectively, and we can also change the first and the second fundamental forms. So the first and second fundamental forms become A bar and B bar. So A bar is simply is only a function related to S, but B bar is a function of both the rotation and the scaling matrix. So we know the modified fundamental forms, and now we need to find elastic energy to solve in the third equilibrium to get the final output. And here we are following this 2018 paper from Chen's group and also our SIGGRAPH Asia paper last year. So actually, from our perspective, this is quite a good essential simulation model or closed simulation model compared to the common hinge-based banding model. So you can see the first term, this one is the stretching energy, and the second term, this one is the bending energy. So actually, this equation is quite elegant because it unifies the stretching energy and the bending energy together. And you can see it naturally incorporates the plastic fundamental forms. And W is the energy density, and E is the total elastic energy, by the way. So A bar and B bar here are the plastic fundamental forms in the previous slide, and they are the function of R and S. And just as I said before, A bar and B bar are usually inconsistent globally, so they cannot be perfectly achieved. And so that's why we need to solve the optimization to find the closest consistent match, A tilde and B tilde. So A tilde and B tilde, they are the output fundamental forms, and they are the functions of the output surface positions X or the output match positions X in the discrete configuration. So to summarize, in this slide, we are trying to build up the relationship between the RS degree of freedoms and the output match positions. So given an arbitrary R and S, we can solve this argmin optimization to get the corresponding output match positions. X is our final output. Okay, so here I would like to show an interesting experiment. So the neutral shape is a Stanford banding, and we have only 2 positional constraints. So one positional constraint is on the bottom left, and the other one is on the top right. And we got these 2 positions by uniform scaling the Stanford banding 1.5 times larger in Maya. And you can see, just given these 2 constraints, our method can discover such a perfect uniform scaling. And you may think it's quite naive, but it's not. So here we have a comparison to our comparison of our method between to the ground truth. So you can see they are very similar, but we run this experiment in previous method. For example, shape up and as rigid as possible and primal. And for the shape up, as the reviewer required, we even implemented the shape up with varying stiffness. So the shape up has the strongest stiffness near the positional constraints, and they also suffer from the shearing artifacts. So actually, it's quite difficult to achieve in the previous method. And this is the optimization procedure of our method. You can see our method gradually grows the whole Stanford banding to meet the final positional constraint. But we also try the degree of freedoms from other papers, and they cannot make progress in the optimization. And this is a detailed comparison. So in our work, we use a spatially varying R and S as our DOFs. So S is a 2 times 2 matrix, and for the results, our method can discover such a uniform scaling. And there is a paper in 2018, and Chen and his colleagues proposed to use arbitrary A bar and B bar as their degree of freedoms. So A bar and B bar are just 2 arbitrary symmetric matrices. They are not related to each other. And so this is actually our initial idea. We implemented their paper and plugged the degree of freedoms into our framework, and it gave us a broken mesh. So we spent quite a lot of efforts to figure out why it didn't work. So it turned out that our perspective for this one is that you should satisfy the local compatibility, which means the Gauss quality equations. But arbitrary A bar and B bar, because they are not related to each other, they cannot satisfy such a Gauss quality equation. So you cannot even guarantee that such a surface even exists locally. So that's why the mesh is broken. And there is another paper in 2008. Kircher and his colleagues proposed, just as I said before, this is a standard polar decomposition. You just do the polar decomposition of the local frame D, and you get this rotation and the scaling matrix. And you have, so this here, S is a 3x3 matrix. It has more degree of freedoms. And we also implemented their paper and plugged the dots into our framework. And it turned out that the optimization didn't make any progress. Also, we have some self-intersection on the bending ear. And our insight for this failure is that their degree of freedoms are not decoupled as cleanly as ours. So you can see we have a very detailed analysis in our paper, and you can refer to our paper for the details. Next, I will introduce the surface discretization to triangle meshes. So here, actually, we just follow the previous work, so nothing special here. I will just introduce quickly. This is a parameterization of the triangle, of each triangle. So for each triangle, we regard it's a mapping from the canonical triangle to the deformed triangle. So here, we should notice that Ni, Nj, and Nk. So these three yellow normal vectors, they are not simply the triangle normal. Actually, they are the mid-edge normal. Which means they are the average of the normals of the face incident to that edge. And then we can define the discrete fundamental forms accordingly. So we define the fundamental forms on each triangle. And the W is the elastic energy for each triangle, and the total energy E is just a summary of the contributions from all the triangles. All right, so in the discrete configuration, here is a modified plastic fundamental form related to R and S. So A bar in the discrete configuration is a function of S. And for B bar, it's a function of both S and R. So here actually is quite interesting because in our paper, we give an analysis of this S and R. We claim that this is the most cleanest way to locally deform a surface. So S, actually, they are the intrinsic degree of freedoms. So S will influence both the first and the second fundamental forms. And R, they are actually the extrinsic degree of freedom. So they will only change the bending behavior of the surface. So they will only influence the second fundamental form. And for this N bar I and N bar J, they are the mid-edge normal I introduced before. And in practice, we calculate them by applying element-wise differing rotations. For example, we have different rotations on this triangle pair. And first, we rotate their normal vector and then do the averaging to get the new mid-edge normal. All right. So now it brings us to the as smooth scaling as possible shape optimization. I think my professor told me yesterday that this is the most important slide in the presentation. Yeah. So for the first equation, for the first line, this is the objective function, and for the second line, this is our subject constraint, the condition. So actually here we are searching the R and S space to find the smoothest RS to generate the output mesh that satisfies the user constraints. And for the first term, this epsilon x is the quadratic energy for the user positional constraints. And in general, it can be replaced by any user-defined regularization term. For example, this epsilon can be the volumetric, can be the volume of the mesh or the area of some specific region. And this L is a mesh Laplacian operator to enforce the smoothness of our R and S. And if our R and S are spatially varying smoothly, we can plug this R and S into this argmin, this second line argmin optimization to get a smooth output mesh. And this E is the elastic energy after incorporating the plasticity we just introduced previously. And this P is a condensed vector for the R and S of all the triangles. X is the output mesh vertex positions. So just as before, this this term enforces the smoothness of R and S. So the smoothness of R and S will lead to a smooth output positions by solving this argument problem. So the second line is simply solving the sturdy equilibrium under R and S. And in our final revision, we add this third term, this beta term. It's a P minus P0 squared. So this P0 is an identity plasticity for the input mesh, which means for all the rotation matrix is simply an identity matrix, and for all the scaling matrix is also an identity matrix. So we call this term similarity to the input mesh. So this is optional, but we add this and we regard this as a new feature because the user can finally tune the parameters to get different smoothness of their results. And the other reason is that this term can also improve the numeric performance because the second derivative of this term is simply a diagonal matrix. So it will greatly improve the condition number of the Hessian matrix for the objective function. And we used a Gauss-Newton solver to perform the optimization and see our paper for the mathematical details. And as I just said, we introduced the third term, this beta term. So we have two parameters. And so this gave us space to play with alpha and beta. And now we have an exploration for an alpha and beta. So alpha is a smoothness term, and we cannot remove it. And so we can gradually increase beta from 0 to a relative large value relative to alpha. So you can see in this experiment, the neutral shape is simply a sphere. When we set beta is 0, which means we have no penalization or no bias to the input mesh, and we get a very smooth ellipsoid. But if we gradually increase beta relative to alpha, you can see our shape will become sharper and sharper. And actually, we observe the same sharp artifacts in the previous works. So this explains why the previous method will fail for this kind of scenario, because they always penalize the difference to the input mesh, so they will always have sharp artifacts near the positional constraints. And of course, if we set alpha to be 0, this problem will be ill conditioned because there is no regularization. So this will give us a very ugly shape. All right, finally, it's our definition of L to measure the smoothness of the rotation and the scaling field. So for the scaling, because it's a 2x2 symmetric matrix representing scaling in the parameterization domain, we cannot subtract them directly because they are usually in different directions. So our algorithm is that for each triangle pair, we first unfold them into the same plane and use a matrix similarity to measure the difference. So this is exactly the concept of matrix similarity in the linear algebra. And for the rotation, we use the Rodriguez formula to use a 3-length vector to parameterize the rotation. And here, for simplicity, we just subtract them directly. But I need to acknowledge that this is the limitation of our paper, that if you are familiar with the Rodriguez formula, you will find if you just subtract the rotation directly, and if you apply a global rotation to your mesh, this smoothness energy will be non-zero. So this will lead to a big increase in your smoothing energy. So this is kind of like a limitation. And our solution in the paper is that if the user wants to apply a large global rotation to the mesh, you should first align the mesh with the user constraints, which means we have a pre-processing procedure. And our smoothness energy is always 0 for the uniform scaling, and that's why our method can discover a perfect uniform scale under only 2 user constraints. All right, here are more results in 2D. So for this gingerman, we can just use 5 positional positions to pose this gingerman into different posture. And so here we compare our method with the shape up. So you can see our contour are almost the same, but our method produces a quite good quality of the mesh. But for the shape up, it produces the self-intersection. And our method can not only handle the positional constraint, but also the rotational constraint. So in this checkerboard, we have a rotational constraint for the middle square. And you can see under different boundary conditions, our method can produce different smooth patterns. And here is a 3D example. We are trying to grow the middle part of this bending tube. So here is a comparison to the shape up and rigid post one primal. For the shape up, we even, so at the reviewer request, we even tried the triangle string constraints and the similarity constraints, and either of them produce volume shrinkage. And here is a comparison for the horse example. And here we are trying to compare our method with within a very naive forward simulation, because in our review procession, some reviewers complain to us that you can just increase the bending stiffness and run a forward simulation, and you will get rid of all these artifacts. And also, and so we implemented what exactly as the reviewer requested. And so here you can see so gamma here is a ratio between the bending energy to the stretching energy. So even we set the bending energy to be 1,000 stronger than the stretching energy, it still creates sharp artifacts. And this is a comparison to the previous works. All right. So for the future work, I think the first direction is that how can we get rid of the double argument optimization? Because as you said, as you can see in our shape optimization side, the equations are quite heavy, right? So we need to solve double argument optimization to get the results. And so our performance is quite slow comparing to shape op. We need to admit that this is a drawback of our method. And although our method can produce smoother results than the previous method, but it's much slower. But comparing to the volumetric mesh method, we are still faster because we have fewer degree freedoms. And the second direction is that how to apply our method to the SGP problems. Because for the shape matching, actually, our method can grow the meshes without a volume shrinkage or without a sharp artifact. So I think it's quite interesting to see how can apply this kind of idea to the IPC problem to strengthen the current SGP pipeline. And the third direction is that how to apply our method to the curves, because for the curves in 3D, it's simply another kind of co-dimensional object. And the final direction is that how can we improve the numerics when not using the similarity to input match term. So the similarity to input match term, so here we are saying that the beta term. So without the beta term, we can still solve our optimization, but because of yield conditioned Hessian, the convergence speed is quite slow. So how to improve the numerical performance is also another interesting direction. Thank you for your attention.
You said that your method preserves uniform scaling. What about non-uniform scaling? If you have affine mapping, you fix one point and you deform it non-uniformly. Would you preserve it also?
Pardon?
You said that your method preserves uniform scaling. So I'm wondering what happens if you will have non-uniform scaling. So in 3 directions, you will scale by different factor.
Yeah. So first of all, maybe I emphasize this experiment too much. So for this experiment, I mean, under only 2 positional constraints, we can do uniform scaling. But for example, for the fish, actually we are doing non-uniform scaling for the different regions of the mesh. I guess you are asking that if we apply only 2 positional constraints, how can we achieve a non-uniform scaling, right?
Well, you fix one point and then you move 3 linearly independent vectors arbitrarily, right? Affine mapping in 3D. You take a cube and you map it to a parallelepiped. Because here you have way too many points. Yeah, this is overdetermined.
Yeah, so here we have many undeformed positional constraints on the mesh because we want to show that our method can not only grow the mesh but also shrink the mesh. And so because we have this kind of, let me see. Because we have smoothness energy in the optimization, so even the scaling is non-uniform, this penalization, this smoothness term will also try to enforce this scaling as smooth as possible.
Okay, yeah, but that doesn't answer my question, but never mind, we can discuss it offline.
All right, thank you.
I think I will ask one question. So, it's very popular to use the caging in industry to manipulate the shape. How to compare your method with just use the caging with tuning?
Yeah. So with the skinning, actually, we haven't comparing our method. We haven't compared our method with the skinning, but I guess for the skinning, it's hard to exactly specify. For example, in our problem, we can just so given some indexes, we can stretch the mesh to the specific positional constraint. But for skinning, I guess it's kind of hard to define such an energy. And also, this quadratic term can be replaced by any geometry related regularization term. But I guess for skinning, it's kind of, for me, I think it's kind of difficult to imagine how to define such a regularization term.
Yeah. So I mean, if you can build a cage and then you can drop the cage and make.
Yeah. So for the cage method, I think you will be able to deform the mesh smoothly, but as I said, this kind of problem is focusing on the large string. So I guess we will still suffer from some kind of artifacts. Yeah. Thank you.
Oh, hi. So very nice talk. So I have a question. I wonder, do you ever try like a naive approach, which is like maybe you just say optimize the bi-Laplacian energy and subject to use user constraints?
Yes. So for the bi-Laplacian, we also try such an idea, and you can refer to. So I didn't show here, but you can refer to our paper that this kind of idea will also suffer from sharing artifacts, like I showed for the. Like I showed for here. So it will also suffer from similar sharing artifacts for this kind of case. Yeah.
Makes sense.
Right. If no more questions left, then I'll start again. Yeah.
Thank you.